Hey guys, welcome to my channel Harshu Education, and today we are going to talk about queue data structure. So queue data structure is FIFO type of structure where whatever goes first comes out first. So it is exactly like a queue in real world. So in a queue, if you're going in a queue to, let's say, to pay for electricity bill, so if you come first and get in the queue first, you will be able to pay for your electricity bill first. So it is like first in first out. So whoever comes first will be going out of the queue first as well. So exactly opposite of stack. In stack we had like last in first out. So whoever was coming last was going out of the stack first. But here we are doing like whoever comes first will be going out of the queue first, exactly as in real world scenario. So the queue has so for queue, what we keep in mind always whenever we are doing queue implementation for any type of for our data structure, we'll have to make sure that insertion or addition in a queue must happen from one end, that is the rear or tail of the queue. So in at the rear side you'll be inserting any element. So if you want to insert any new element in your queue data structure, you'll be inserting it at the rear end, whereas if you have to delete it, you will delete it from the top of the queue. So that's why when you're doing queue data structure, let's say if you're doing it with linked list or array, you have to keep two pointers, one for front and one for rear. So front will hold pointer for the element which are being added at which are being deleted from the front, and rear will keep pointer for element which has to be added in our queue from the back of the queue, like from the rear side of the queue. So again, queue has these operation as we had in stack: enqueue or push, dequeue or pop, front or peak, or and is empty. So push, pop, and peak is actually more famous in context of stack. In queues, we call it enqueue. Enqueue means inserting in the queue. Dequeue means deleting from the queue. Front means just peeking the first element of the queue, and then is empty will return you whether your queue is empty or not. So similar to stack, queues operation should always happen in O of 1 times, means it should always be happening in constant time only. It cannot take logarithmic or linear time. It should always happen in constant time. So we'll see how we can implement queue in Swift using array and linked list today. So let's implement queue with array. So let's create our class and we'll call it queue, and we'll make it generic so that we are not restricted to any data type like string or int. And then as I said, in array based implementation you have to create an array. So I'll create an array, and that will be of type T. That's all. Our array is ready. Now let's create a function enqueue. This would be to insert any element in our queue. So this will take a parameter of type T, which is our data type. And then very simple, as we did in queue, as we did in stack, we just append our new element in our queue. So that will append at the tail of your queue. And now to pop, so pop is called dequeue in our queue data structure. We don't need any parameter, and the return type will be T, which should be optional because our queue can be empty as well. So if we can check over here, if our array is empty, then return null. So we already have an is empty function in our array. else we will do return and then arr dot remove at 0 index, because we are removing from the top of the queue, like deletion must happen from the top of the queue, so that's why. So NQ and DQ are the most important functions. For peak, like for front of the queue, if to get the front of the queue, you can just return the first element. Like instead of removing, you'll just return our first element. So I won't be implementing that. So let's just call our queue and see if our NQ and DQ is working or not. So let's call var queue of type, I'll create string, and let's enter some NQ something in our queue. NQ, I'll say hi, NQ dot NQ, I'll say there. Now let's dequeue and see what happens. So yeah, so we have high and there, and because the first element was high, this is high is now being dequeued as well. So when we call dequeue, it's calling this the first element which we enqueued first. So in case of stack, if it was stack implementation, the last element would be removed from the stack, but in queue, it removes the first element from the queue. Okay, now let's do linked list implementation of queue. So let's do class and then LLQ. So that would define our linked list queue. So in our linked list, we have data and address of the next node. So let's create that. I have data and I don't want to specify my data of like any specific data type, so I'll make it generic. So let's make it data of type T, and then var next would be our address of the next node for our linked list, right? So we'll call it LLQ, and this would be optional. So let's initialize our data with a value of type T data type, and then initialize our T with the value. Okay, so this is our queue linked list node. So so this is actually our node implementation, linked list node implementation for queue. So each node will have data and address of the next node. Now let's implement our queue using linked list. So let's create another class and say LLQ. I'll call it implementation, and again I don't want a data type specific, so let's make it generic. And then so as I said, for queue you need to have front, rear pointers. So we'll do that, and then we need to know our head of the linked list as well. So let's create a variable called head of linked list type T, and this would be an optional. And then let's create create one more variable called front, again of same linked list type T. This will be optional as well, and I'll return head as our front. So head is nothing but our front itself, and then var rear would be the last element in our linked list. So rear LLQ of type T, that would be optional as well. And let's return rear. So whenever we are creating a linked list implementation for queue, we will need to know what is the last element, what is the last node in our linked list like here. So what is the last node in our linked list? Otherwise, if you don't do that, you will have to traverse through the linked list to insert a new node, which will break our queue data structure rule that it should always happen in constant time. So if you traverse through the linked list to reach to the end of the node, then it will take O of n time. So that would break this rule. So that is why whenever we are creating our linked list, at that time itself we will take a reference of our rear end of the we will take a reference of our last node in the linked list. Then only you can insert uh, new node after your last node, because you have reference to your because you already have reference to your last node, so you don't have to traverse through your linked list. So to do that, uh, of course, like at the time of implementation, like before even calling the push operation, we'll just get a reference to our rear node in our linked list. So to do that, let's create a node of, and let's initialize it with head. This would be of type LLQ node itself. And then what we'll do is we'll just traverse. This is our node, head node, right? So we'll just traverse through our this head node. So and then whenever we reach to the end, we'll return that node as our rear node. So to do that, let's do a while loop, and we will write like node dot next is not equals to null. So as long as node dot next is not equals to null, we'll just keep on traversing node dot next, and then once we have that, we will return the node. Come on, not road, it's node node. So this node will be our last node in the linked list, right? So why I didn't just traverse through the head, because I didn't want to change my head. So that's why I created a new variable node and assigned that variable with our head node, and then traversed that variable so that I'll have last node in this temporary variable, and don't tamper with my head node, which I'll be using further. So let's create our function enqueue. This will take a value which we'll be pushing in our queue, and there won't be any return type. Okay, so as I said, you need to have last node to enqueue any node, right? So we already have rear, so we'll just check if let's name it last node and rear. So if we'll see if rear has last node, if last node is there, then our work is very simple. We'll just insert our new node in the next of our last node. So every last node of linked list will have next. This next will be null for every last node. So instead of null, we'll just enter our new node in this next. So let's create a new node, LLQ val. Okay, so this is our new node. I can just create this node outside the if loop, so that I don't have to create it in the else condition. So new node, so new node, and then we just assign that new node to our last node, right? And then in the else condition, if our rear doesn't have any value, it means our queue is empty, right? So I don't need a question mark over here because I have unwrapped it already. So if it is empty, then what we'll do is we'll just put in head node, our new node. So then it means our head node is empty, and then it means uh, our new node would be the head node. So we'll just initialize head node with new node. So this is our push operation. It is saying that it doesn't have to be variable because we are not changing it anywhere. And then yeah, so this is all we have to do for enqueue. Just create a new node first of all, and then if you have a rear node already, which you must have if you have written over here. So if there is values, there is nodes in your linked list, then it will then we'll have last node, and in the last nodes next we'll just assign our new node, right? And this new node next doesn't have to be assigned because it will always be nil, because that is why it is the last node. So this new node will become last node, right? And if last node is not there, then we'll make this new node as our head node itself. Now for dequeue, we don't need to pass any parameter, and we'll be returning t of nullable. So again, in this we first check if our head is null. If it is null, then we just return null because we don't have to dequeue anything. If it is not null, then let's first create a uh, uh, you know temporary head. So we'll just keep our head node in our temporary variable, and we'll keep our head node in temporary variable, and we'll just traverse to the next node. So what we are doing is we are just removing the first node from our linked list, right? So we have to remove this from the linked list. So as we did in stack as well, all we have to do is in our head node next, in our head node we'll just put the next of the head node. So what we have to do is let's just do a check if head nodes next is not equals to null. If it is not null, then in head node we'll just put head nodes next. So the next element to the head node will become the head node, right? And this will make sure that our head node is removed. If our next head node's next is already null, then we'll just make our head node null, and that is all. So it means that if our head node next is null, it means that we only have one element in our linked list, one node in our linked list. So we just which is the head node. So we'll just make head node as null. And then for this return type, as we have already stored our current head node in temporary variable, so this temp will give you the current returned value, right? So it would be data. That's all. So for dequeue, you just check if head node is null, then return null. If head node is not null, then just keep your head in a temporary variable. Keep your head node in temporary variable, and then just move the cursor to the next. Move the head node to the next node of the linked list. So what I'm doing in this line is just moving this head node to the next node over here. So head node will become the next node of the linked list, and if head node's next is null, it means that we only have one node, which is the head node, and then we will just make it null and will return the temporary data. So let's test it. So variable LLQ equals to LLQ implementation. Let's make it int. and then LLQ dot NQ. Let's enter 1 and then 2. So first value to enter in our queue is 1 and second value to enter in our queue is 2. So when we do LLQ DQ, so first value will be dequeued. DQ, so this should return 1, and then we haven't done any peak. I can do peak as well. So peak will basically return our head node. That's also, I can just write it. Peak T return head dot data. So I can do LLQ dot peak. So after this DQ, peak will become 2. So 2 will become top of our queue. Okay, that's correct. So we have two values entered in our queue, and on DQ it's removing the first value which was entered, and then on peak it is giving me the second value which has become our top node now. So this was linked list implementation and array implementation for queue data structure with Swift. I will leave the link for this code in the description below so you can see that. Yeah, that's pretty much it. Thank you so much for watching. Bye bye.